Now let's talk about linear combination, a very important concept in linear algebra. So far we have defined three operations: vector addition, the scalar multiplication, and dot product. The result of dot product is not a vector, it's a single number. So in order to create new vectors from existing vectors, we have two operations: vector addition and a scalar multiplication. Linear combination is using these two operations to create new vectors. Assume that we have a two-dimensional vector u. So we can multiply u by a scalar or add u to itself. In this case, you can factor out u, and again, you can get a scalar multiplication. So when you have just one vector, performing linear combination is equivalent to a scalar multiplication. As you might remember, a scalar multiplication of a single non-zero vector gives us vectors on the same line of u, either in the direction or in opposite direction of u. Equivalently, we can say a single non-zero vector spans a line. We can get anywhere on that line by linear combination. Okay, what about when we have two vectors in two-dimensional plane? The question is where we can go by linear combination of these two vectors. Let's pick a random point in the plane. Can we go there by linear combination of u on w? This is equivalent to saying, is it possible to create a vector which its tip is at that point? I want you to pause the video and think about this. The answer is yes, we can get there by linear combination. First, we need to scale u on w and then add them up. So from this example, we can somehow conclude that we can go anywhere in the plane by linear combination of two vectors with different directions. Saying it differently, two vectors with different directions span a whole plane. A related concept to linear combination is linear dependency, and the opposite of it, linear independency. Assume that we have a set of at least two vectors. If we would be able to write one of these vectors as linear combination of the other vector, we would say that vectors in this set are linearly dependent. Otherwise, these vectors are linearly independent. Now let's look at the geometry of linear dependency. Imagine two vectors lying on the same line. Obviously, you can write one of these vectors as scalar multiplication of the other vector. So two vectors lying on the same line are always linearly dependent. Now consider two vectors lying on different lines, which means different directions. Are these vectors linearly dependent or independent? You can easily realize that you can't write one of these vectors as scalar multiplication of the other vector, because by scalar multiplication, we can't get out of the line where the vector is lying. So in this case, v and u are linearly independent. We can say two vectors with different directions are always linearly independent. What about three vectors with different directions? Remember that we can span the whole plane with two vectors in different directions. So this means that we can write the third vector as linear combination of two first vectors. So when we have three vectors in two-dimensional plane, they are linearly dependent. We can generalize this rule. When we have more vectors than dimension of a space, the vectors are always linearly dependent.